Good afternoon. This is Professor Shannon Gracie. We are working out of the Precalculus Enhanced with Graphing Utilities text by Sullivan and Sullivan. And today we'll be going over composite functions. Understanding composite functions is very important in calculus, so it's good to really master this section, especially being able to decompose a function and recognize the two functions that are composed together. So here we go. First off, let's warm it on up. So we have f at x equal to the square root of x. What is the domain of f? Good. It goes from 0 inclusive to infinity. Or if you do set notation, x such that x is greater than or equal to 0. All right, so what is f at 16? Well, that would be the square root of 16. So wherever you see an x, you would put 16 in this case. And what is the square root of 16? Awesome. It is 4. How about f at a? Well, it would just be the square root of, good, a. So wherever you had an x before, you'd put an a. And what about 5x? Well, it would just be the square root of 5x. So actually, what you've done is you have actually composed one function with another. If you looked at, say, suppose g at x was equal to 5x, do you see that f evaluated at g at x would be the square root of 5x? So what we actually found was f composed with g at x. Okay? So that's what we'll be talking about today. So these, of course, were the answers that we had gotten. Now, what must be true about x in part 3 and actually a in part 2? They both would have to be good, positive. So x would have to be greater than or equal to 0, and a would have to be greater than or equal to 0 from part 2, and this guy from part 3. All right, so composite functions. Given two functions, f and g, the composite function denoted by this notation here, and it's read as f composed with g. F composed with g is defined by, well, f composed with g at x is equivalent to f evaluated at g at x. Now, the domain of f composed with g is the set of all numbers x that are in the domain of g such that the output g at x is in the domain of f. Okay? So here's a little, visual, if you will. So let's suppose that you have, let's consider the domain of g and the domain of f composite g. So if you consider kind of, I don't know, we could make sort of a little blob here. And then we can just separate it. And so if you consider this part here, the domain of g alone, okay? This part is the domain of g alone. And if you then consider this other part here, where it's still the domain of G, but it also has a special property that it is the domain of both. So this lighter blue would be the domain of the composite function. See, isn't it fun? You get to color in math. All right. So this is what we have going on. So this here, up here, the darker is the domain of G. So you have some x value in here, and you have some other x value in here, and this happens to be the domain of F composed with G. Okay. Now, if you consider kind of an intermediate circle here, or blob, I don't know why they always do blobs, but if you consider sort of an intermediate blob here, where this is the range of G, and then again we're going to divide it a bit into an overlap that would also be the domain of F. So that's range of G, and this is domain of F, okay? Now, these x values, this x value from the darker blue shaded area can go to either part of this. So this here, let's get back to our highlighter. So this here, this part right here is range of G. So you've got G can go, you know, the x values can go anywhere here. So now, in this other part right here, you get, again, this lighter shade that we had used. Right here would be the domain of F. And sorry, we'll get this going in a moment. Probably should have pre-prepared these. And then, so basically, if you have an x value go over here and end up here, what you have is you have G evaluated at that x value. So this is the function G. Now, again, if you have a jump here, sorry, I was supposed to go one more. If you have a jump here where you're still in the range of G, right? So you still have G evaluated at some x, right? But it also happens to be in the domain of F. So not all output values for G will be in the domain of F. So we just have to be careful about that. So now if you just kind of go over here and make one more little blob, then what will happen is this here, the bottom part, would be the range of F composed with G. And this would be the range of F alone. So the range of F alone will just be some, oh, and my apologies, I forgot to draw one more spot here. This was the overlap, and if you consider this to be the range or the domain of F, And this part of the domain of F does not overlap with the range of G. So we'll just do a different coloration here. Do it green. And we'll have something like this. And then the range of F composite G, again, will be that light blue. So here we go. Here's the big picture. So that is the range of F alone. This bottom half is, so this whole thing is the range of F alone. Okay, this whole thing. But this blue happens to be the range of F composite G. Just like this whole piece right here comprises the domain of F alone, but it also happens to comprise the range of G in the overlap. All right? So here we go. If we have this go from here and bounce over to, whoops, go from here and bounce over to here, what you've gotten was F evaluated at G of X. So basically an output of G, which is in the domain of F, can yield an output for the range of F composed with G. Okay? So basically this here, since it feeds to outputs for G at X, can be a domain value from G that goes to F composed with G. Okay? Okay, so here we go. Here's a couple of functions. So F at X is negative X squared plus 3, and G at X is 1 minus X. So they want us to find F composed with G evaluated at 1. So this would be equivalent to F evaluated at G at 1. So what is G at 1? Well, G at 1 is going to be 1 minus 1. So wherever there was an X, I plugged in a 1. So here, that is G at 1. Okay, so far? So this would yield a result of F evaluated at 0. So that 0 is a range value for G. Well, now we go to F, right? So we're inputting this range value from G into our function for F, right? So we'll have, this will equal to negative 0 squared plus 3. So we plugged in the 0 we got from before, and at the end of the day we get 3. Okay, so far? All right, so now it's switching around. We're taking G composed with F evaluated at 1. So now it's going to be, this will be G evaluated at F at 1, which will be G evaluated at F at 1 will be negative 1 squared plus 3. So now, n for f, which was here, we're plugging in 1. So that will give us equal to g evaluated at, I think we'll get 2 here. And plugging that in for g, that'll be, remember g was 1 minus x, so we'll have 1 minus 2, which is -1. Okay, so far? All right. So now f evaluated at, or this will be f composed with f at -2. So just on the side, I'll put what f was originally. Remember that f at x was equal to negative x squared plus 3. You can double check that here. And then for the next one, I'm going to write g at x was 1 minus x. Okay, so now this is equal to f evaluated at -2. Kind of strange, but it's okay. So plugging in a -2 for x, in fact, if you want, you can do it on the side here. I'm just going to do it here. That would be f evaluated at the opposite of -2 squared plus 3. So right here, this is f at 2. So now we'll get f evaluated at, that'll be -4 plus 3 is -1. So plugging in -1 to f, we'll have so that'll end up being, I believe, 2. Okay, so far? All right, so next up, we're working with g. So this will be g evaluated at -1. So g at -1 is 1 minus -1. That's my g evaluated at -1. So then we'll have g evaluated at 1 minus -1 is 2, which will give us, plugging it in, 1 minus 2 gives us -1, and we're done. Okay, so continuing to work with the same function, but doing it in general. So in terms of x, let's do these here. So f composed with g at x means that we'll have f evaluated at g at x. So g at x is good, 1 minus x. And plugging that into our function f, we'll have negative something squared plus 3. This something squared is 1 minus x. So that will give us negative. So squaring a binomial means we'll have 1 squared minus 2 times 1 times x, and then plus x squared plus 3. So 1 squared minus 2 times 1 times x plus x squared. So that'll give us, let's see, -1 plus 2x, I'm distributing the negative through, minus x squared plus 3. And so putting these in descending order, we'll have negative x squared plus 2x plus 2, and we're done. Okay, so g composed with f at x. So now g is on the outside. So g evaluated at f at x will give us g evaluated at, remember f at x was negative x squared plus 3. That'll give us G, or wait a minute. We know G. So G was 1 minus x. So in substituting in for x, I'm putting negative x squared plus 3. So you replace x with the function negative x squared plus 3. Simplifying, we'll have 1 plus x squared minus 3, which gives us a result of x squared minus 2. Okay, so far? Awesome. Now, f composed with f at x will be, this is f evaluated at f of x. So f evaluated at negative x squared plus 3, because that's what our f of x was. So now we're going to plug in negative x squared plus 3 squared plus 3. So my function f, remember f of x was negative x squared plus 3. So I plugged in f of x into our function f, and we end up getting this. So it's kind of crazy, but also kind of cool. So again, squaring a binomial, this is going to give me positive x to the fourth minus 2 times 3 times x squared is 6x squared plus 9, and then plus 3. Now I need to distribute the minus through, and I'll get negative x to the fourth plus 6x squared minus 9 plus 3. And we have negative x to the fourth plus 6x squared minus 6. And lastly, second to last, g composed with g at x. So remember that g at x was 1 minus x. So this will be g evaluated at g of x, which is g evaluated at 1 minus x, which will be 1 minus, replacing x with 1 minus x, we'll have it. So this was our g at x. So in for that x, I'm plugging in 1 minus x. And that was what we were doing over here. Okay, so this will be 1 minus 1 is 0, and then negative x is positive x. Okay, so what do you think about that? Do you remember anything about evaluating a function at something and getting x out? Good. It looks like g is its own inverse function, which is also really cool. Okay, so now we're going back to working with x alone. So f at x is negative x squared plus 3. This is really important. This is called the difference quotient. And basically, once you learn about limits, if you evaluate the limit as h approaches 0, you'll get the slope of the graph at x equal to x. So this is what we'll learn in calculus. So the better you are at working with this, the easier things will be. So we need to evaluate f at x plus h. So we'll replace the x in f with x plus h. So right here, we plugged in x plus h wherever there was an x in the original. So this first expression is f evaluated at x plus h minus f at x. So what was f at x? Good. Negative x squared plus 3 all over h. So now, continuing, we'll have negative, when we square this out, it'll be x squared plus 2 times x times h plus h squared plus 3. Distributing the minus in the second expression, we'll have plus x squared minus 3 all over h. So the 3's zero out. And continuing to simplify by distributing the minus, we'll have negative x squared minus 2 times x times h minus h squared plus x squared all over h. Now, do you see the x squareds will zero out? So factoring out an h from the numerator, we'll have negative 2x minus h all over h. So the h's divide out. And at the end of the day, we will get negative 2x minus h. So you can be certain that you'll have more practice with this on the, problem set, and you can be pretty certain that you'll have a exam problem that relates to the difference quotient. Okay. So now getting into the domain. So remember, the domain of a composition is the range elements of the original function have to be in the domain of the most outside function. So the range of the inside function has to be part of the domain of the outside function. So there's a couple ways you could go about this. You could just compose the two functions and find out what that new function is and find the domain. Or you could kind of reason what the domain should be. So if you look at g of x equal to x cubed, the range of the cubic function is minus infinity to infinity. But if you look at this function f, we cannot put any numbers that are good, less than 1 in there. So by kind of reasoning this out, you could say, oh, the domain of this composition would be 1 to infinity inclusive. Or you could say f composed with g at x is the square root of x cubed minus 1. You're replacing the x with x cubed, right? Let me do another step. Sorry. Would be f evaluated at g at x, which would be f evaluated at x cubed, which would be the square root of x cubed minus 1. So then you would say, oh, okay, x cubed minus 1 has to be greater than or equal to 0, which means x cubed has to be greater than or equal to 1, which means that x has to be greater than or equal to 1. Because the cube root of, you could kind of cube root them, right? Okay, so let's write that in interval notation. The domain of the composition. So domain of f composed with g is this. Okay, so here we go. Example 4. You have this quotient and you have a line, so a rational function and a line. So we have to be concerned about, we have to be concerned about a 0 in the denominator. So again, there's a couple ways to go about it. You could figure out what x values to exclude from f, and then figure out what input values of g will yield that. Or you could just say, oh, f composed with g at x is f evaluated at g of x, which is f evaluated at the line x plus 2, which will give us 5 over, so substituting in for x x plus 2, because that's what g is. And then we'll still have that minus 7. So then we'll get 5 over 2x plus 4 minus 7, which is, I'll do another line, which is 5 over 2x minus 3. Then you say, okay, 2x minus 3 can't be 0, so 2x can't be 3, thus x cannot equal to 3 halves. So you would be going from minus infinity to 3 halves union 3 halves to infinity. Okay? All right, so let's look at example 5. So we have f at x equal to x to the 5th and g at x equal to the 5th root of x. So f evaluated at g at x is f evaluated at the 5th root of x, which is f is something to the 5th. This something we're plugging in is this 5th root of x. So that would give us a result of x. All right, going the other way. This is g evaluated at f at x, which is g evaluated at x to the 5th, that's what f was, which is the 5th root of x to the 5th, which is x. So what did you notice? They're the same result, right? So again, like we were talking about before, what does this mean? Well, it means that f and g are inverses. All right. Okay, so next up, this is all about decomposing functions. So we're looking at this h of x. Let's let h at x equal to f evaluated at g, actually I'll do it in different colors, f evaluated at g at x. So what should we have that inside function be? What should g at x be? Good. G at x is the 1 plus x squared. All right, that's what's being plugged in inside the most outside function. What about f at x? F at x is something to the 6, right? So the way you would do that is just write x to the 6. Can you kind of visualize if you evaluated f at g at x that you would get h at x? So we're done. Okay, you try the next one. See how you do. Again, you can let h at x equal to f at g at x. All right, let's see how you did. So what would our g at x be? Perfect. G at x is 5x minus 8. And what function is g inside of? It's inside of the absolute value function. So there you go. You just decomposed a couple of composite functions. So when you learn how to integrate and differentiate in calculus, these are very valuable skills. Okay, here's an application for us. The spread of oil leaking from a tanker is in the shape of a circle. If the radius r in feet of the spread after t hours is r at t equals 200 times root t, find the area A of the oil slick as a function of the time t. So let's think about this. Area of a circle is pi r squared. So area in terms of time would be equal to pi times r at t squared. But what was r at t? Good, it was 200 times the square root of t. So when you complete that, you'll have a at t is pi times 20,000 t. And prettying it up, we have area at t is, oh, not 20,000, 40,000. 40,000 pi times t. All right, so that wraps up the lesson for today. Make sure you do some of your problem set and have a fabulous day.